is a form of energy. First form is a form of energy. Mathematically, it can be defined as work is the product of force and displacement. Force and displacement in the direction of force applied. Clear? Mathematically, work is defined as the product of force and displacement in the direction of force applied. In the direction of force applied. Okay. Now I am going to write dW is equal to F into dl. The thing is, while we discuss force, I can write directly F. While we discuss pressure, I can directly write V. But in case of work, you should not write directly W is equal to force into displacement dl, because work is a path function. Work is a path function. Clear? Moreover, both work and heat are energy in transit. Energy in transit. Because they can be stored permanently in the system. They are path function. Hence, this is the right form. Okay? Again, dW is equal to force is nothing but pressure at the cross-sectional area, because pressure is equal to force per unit area. Hence, I am going to write force instead of pressure into cross-sectional area. Again, dl, the volume change for a constant cross-sectional area, the volume change is included dV divided by cross-sectional area. This is volume, this is cross-sectional area. Meter cube divided by meter square is equal to meter. Meter is the unit of length or displacement. Area gets cancelled. So dW is equal to P into dV, or you can write like this: W is equal to P into integral dV limit V1 to V2. Limit tends to V1 to V2. Okay. Now let us see W is equal to P into integral of V1 to V2 to dV. What about the value of W? If W is the positive value, W is the positive value. This is expansion process. This is expansion process. Expansion of gas. When W is equal to negative value, this will be compression process. Now I am going to use a simple expansion of gas example. Simple example. Expansion of gas. Let us see here. See here. This is the piston cylinder arrangement. Piston cylinder setup. The piston is a frictionless. Consider piston is the frictionless. That one mole of a gas is enclosed by the piston in the cylinder arrangement. Let us consider one mole of a gas is enclosed by the piston in a cylinder. Now assume that the gas starts to expand. Before that, outside of the system, this atmospheric pressure. Outside of the system is atmospheric pressure. Hence, pressure inside the system will be 1 atmosphere. Let us consider 1 atmosphere. Pressure is P1, volume is equal to 1 meter cube. P1 given. Upon expansion, there is no block to resist the piston in the opposite direction. Hence, the piston moves freely. Once again, pressure is constant. The final pressure is constant, but volume gets increased, expanded. V1 initial volume, V2 final volume. Initial pressure P1, final pressure P2. Final pressure, there is no against force, counter force to push the piston downward. Hence, again pressure is 1 atmospheric pressure. Pressure is constant. For this case, the PV diagram is, this is volume in x-axis, pressure in y-axis. See, initial volume, initial pressure, so it will be 100. In this process, expansion process, pressure is constant, volume goes to increase. This is V1, this is P1. Pressure is constant, but volume is increased to a next level. So, this is V2. So, the shaded area under the curve is amount of work done, that is P into integral V1 to V2 dV. This is the case 1. Now another case, pressure is constant, volume is also constant. Upon expansion, pressure inside the system gets decreased. Subsequently, volume goes to increase. Here, pressure P1, upon expansion, pressure goes to decrease, the level of P2. Volume goes to increase from V1 to V2. Here, see this PV diagram. Initial pressure P1, upon expansion, inside pressure goes to decrease. Pressure goes to decrease to P2. Volume goes to increase V2. Decrease in pressure, increase in volume. For such case, this is the amount of work done. That is P dV, integral P dV, W, work done. This is the PV diagram for work done.